There's a little bit of history behind this talk. I was sponsored by Microsoft to go to Seoul, South Korea, where I presented this talk. And as a token of gratitude for that opportunity, I'm here to present it to you on the behalf of Microsoft tonight. So we are recording this. I will be putting this up on YouTube, on my YouTube channel. I have that at the end of this talk. If you're really keen, for instance, I did also record this when I was in Seoul and I've already put it up. I've received feedback about the talk, so while the slides are more or less the same, I will be embellishing it a bit more and speaking at a normal pace. Because I was in a foreign country, I was trying to speak slowly and give time for the interpreter to catch up. So because we're in Melbourne, I'll have some more time to tell some stories, give some more examples, and generally have a bit more fun with it. So that's not the right button. As I said, the title of my talk is Pitfalls in Machine Learning, but another way to view it is what you should learn from my mistakes. I have a PhD and an MBA. My PhD is in electrical engineering, which isn't quite rocket science, but it's close. I keep pressing that button, not that button. So I'm educated in both technical fields and business. My PhD is in electrical engineering. I have an MBA. I've worked in a variety of industries. Most recently, banking and credit risk. I've worked in defense, missiles, rockets, and biomedical engineering, where I was working with Bionic Vision Australia. And I can honestly say that my proudest achievement on a professional level was I wrote the prototype code for the Bionic Eye, which you may have heard about through BVA. So I can honestly say that I've worked on bringing sight to the blind. And I'm here tonight to share some experiences I've had with machine learning projects. I found some inspirational quotes on the internet, such as intelligence is learning from your mistakes, and wisdom is learning from mistakes of your own. Or put another way, wise men learn from others' mistakes and fools from them. So I've worked in 3 different industries, and for each industry I want to consider a separate topic. So for talking about model development, I want to talk about banking or credit risk. In validation, I want to talk about my defense experiences. And for governance is when I want to bring in topics from biomedical engineering. Now, as Chris mentioned, I am a manager of models management. So yes, I'm a manager of management, which is kind of odd. So most of my world now is in the second 2, the validation and governance of models. For many people, when they think about machine learning, they focus on the development. And so I want to go through a larger perspective from my experiences and let you know the pitfalls I've fallen into. And in particular, the greatest pitfall, or the greatest mistake that I've made, is assuming that all the pitfalls will be technical. When in fact, in my experience, that's not the case. So let's talk about banking. Let's talk about developing machine learning models. And while I'm talking about machine learning models, most of these will abstract to other types of models. So if you're using logistic regression, if you're using decision trees, whatever. So I want to talk about an example in terms of credit risk. And I want to have a model for house prices. So why is this important? If a customer has a mortgage with the bank and they run into trouble, the bank may incur a loss based on the value of the house relative to the size of the loan. If you were to look up some keywords, the loss given default, or LGD, is the component I'm talking about tonight. There are others, such as the probability of default and the exposure at default, but tonight I want to focus on this LGD part. This was especially important during the GFC in the United States, and we have a simple model that your loss given default is your balance at default, or your exposure at default, which is that EAD piece, less the house value. So that house value is what I want to focus on. This is a simple model because it doesn't take into account any fees you may have. So if you're going to pay a real estate agent to sell the house, any legal fees, the amount of time it takes to evict the current homeowner. It doesn't take into account reputational damage that you get on Today Tonight, and there's this poor single mother who's just lost her job and now the bank is coming for her house. So there's a lot of things that aren't being taken into account here, but the house value is part of it. And if we look at the experience during the global financial crisis, this is from the US Bureau of the Census, and it's the median house price with respect to time. The shaded areas indicate recessions, and in particular up here during the global financial crisis, you have the period of the housing boom followed by the housing bust. And in particular, if you had a loan of $245,000 at about that time, the recession hits, the customer gets in trouble, the bank takes the house and sells it for $205,000. In a simple case, you can estimate the loss at about $40K. In the US, that's a better model, because in the United States and most states, if you default on the house, the extra $40,000 the bank eats. In Australia, the system is a bit different. Technically, legally, the bank can still pursue you for that extra $40,000. So I'm ignoring the costs of selling the house. I'm ignoring whether or not the bank is going to come after you for the extra $40,000, but it's a simple model. Note it doesn't work the other way. So if the loan value is $205, the customer gets in trouble, can't repay, the house is worth $240. In neither case does the bank keep the $40,000. So while we're talking about modeling house prices, there's a difference as to whether or not house prices are going down or up. If house prices are going up, to a certain extent, the bank doesn't care. But if they're going down, that exposes the bank to loss. So let's have an example. And if you were at my previous talk, it's the same example I used then. I want to use open source data so that all of you can reproduce what I've done. So there's an R package mass, which includes data from Massachusetts. So this is Boston house prices. There's an analysis online in a blog of how to model house prices by fitting a neural network. And I'm following that example so that if any of you want to reproduce this, you can. There's instructions online. And thanks to Michialis for sharing this. So you do that. You get the data, you split it 75-25, you fit this two-layer neural network with 5 neurons and 3. I don't know what you're meant to do with this graph, but here it is. So I fit the neural network. That's what it kind of looks like with all the input variables on the left and all the strengths of all the different connections showing up as numbers coming through. And in particular at the end, this last number is about 1.41. So there it is. So then I would then go out and get new values of the inputs, send it through my neural network, and get an output predicting the median value. Simple. And if you don't think it's simple, well, it's all written up for how to do that. So it's just follow the recipe. No worries. So now we want to have some type of measure of, well, how good is my model? So this is a graph having the observed versus predicted. So if my model were perfect, everything would fall on this line. And you can see that it's more or less following, with a few points that are further out than others. But overall, it looks pretty good. If I make a histogram of the residuals, it sort of looks normal. The peak's around 0. I think my model's pretty good. And so normally now you would take this and run your test data through it, see if there's a difference in your statistics, see if the fit's too different from what it was before, and you would keep going merrily. But what if you don't do that? What if you're looking at all of this from the point of view of a credit risk person, and I see the word logistic here. Now, logistic regression is used in many banking cases. And you might say to yourself, well, I'm doing machine learning. I don't want that logistic there. That logistic just means each one of those nodes in your neural network is a logistic function for each sentence. But I don't want logistic. That's a very simple-minded way of looking at it, but I see the word logistic, that's not what I want. Well, what else could I do? Well, if you look at the options for this function in R, I could also use a hyperbolic tangent. And so I see the word logistic, I don't want that, so I go with the hyperbolic tangent. So it's a single line, it's the same training data, same configurations. I'm going to use the same diagnostics. And now my neural network looks like this. And in particular, I said that last number was 1.41. Well, now it's closer to 0.99. And in general, it shouldn't surprise you that if I change the parameters I use to fit the model, I get a different model. And it further shouldn't surprise you that if I use a different model, I get different predictions. And if I use different predictions, well, they don't quite align the same. They're residuals. The hyperbolic tangent has a bigger peak in the middle, but then the logistic has more that are close. If I were to look at either one of them individually, I'd say they're fine. But there's a saying that a man with one watch knows what time it is. A man with two watches that don't agree doesn't know what time it is. So now the question becomes, well, which one's right? Which one am I supposed to use? And so you say, well, okay, let's come up with some metrics. I can look at the mean squared error and see which one is least wrong on average. Or I can look at the maximum absolute error. So which one is the least wrong ever? And you could nod and say, yeah, both of those, which one of those? And so you look at it, and actually, the logistic has a lower mean squared, or sorry, the logistic has a lower maximum absolute error, but the hyperbolic tangent has a lower mean squared error. So which one of those is more important? What should I do? And there's no reason you should stop there. You can look at percentage errors, you can talk about average percentage errors, you can talk about, well, from the problem statement I care more if it's low than high, so maybe I should take that into account somehow and have some weighted sum. But then you ask me, well, what should the weights be? So here I've got two, and you might say to yourself, well, you've got, if I go back to the analogy of a man with two watches, I have two watches. One says it's 6:15, one says it's 6:30. I know one of them's low and the other one's high, which is which. I'm just going to say it's 6:22. I'm just going to take the average of these. And I'm going to use that as my prediction. And you do that and your statistics improve. So your mean squared error comes down, your max absolute error comes down, and you conclude, well, I've got two, I don't know which one's right, I'll take the average. But you present this in a meeting and someone says, well, wait a minute, I like this hyperbolic tangent one because it's closer on this one. And this is the branch I represent. This is my suburb. And I want the one that's closer. And they make that argument, and someone else says, well, wait a minute, it's further here. I want to use the green one because this is my suburb. And I want the one that's closest for my branch. You can think about it and you're like, well, what if, for these two models, I always picked the best one? Always. And you can say, well, how are you going to know? But if I could always pick which one of these two was best, I would get these. My mean squared errors come way down. My max absolute error is still lower. And I can almost hear the consultants coming to me and say, if I could get it right, I'd have a reduction in mean squared error of 33%. This is fantastic. But I need a way to know which of these models will perform better in every case. And in fact, my residuals are a lot tighter too. And you think about it and you're like, well, there must be some pattern in the data. There must be some reason why my logistic sigmoid, or my logistic activation function, is better than my tangent. Okay? There's some pattern in the data. If only I had a way to classify this pattern in the data, but I've got an idea because I have labeled data. I know which one was less in each case. So I can build a neural network to decide which model to use and achieve this. This is a great idea. Like I can do this. It's the same concept. I just change my neural network from being a regression to a classification, and I have the data, and this is going to be great. Until someone says, well, okay, which activation function are you going to use? Because it makes a difference. That's why we're doing this. Yeah, okay. Okay, so that classification problem has some pattern as to why logistic would be better than a hyperbolic tangent. So I can build a machine learning algorithm to classify which classifier I should use so that I know which regression I should use so that then I can get this down. And obviously you can continue this as long as you'd like. And I say neural networks into neural networks. I haven't seen that precisely, but I have seen neural networks tuning the parameters of support vector machines. I have seen fuzzy classifiers deciding whether or not to increase the number of nodes in a neural network or increase the number of layers. I've seen optimization algorithms over all of these parameters to find the optimal mix. And at the end of the day, you spend a long time talking about whatever machine learning algorithm you're using and very little time talking about house prices. So in the development of these machine learning problems, the first question is this what you want to be doing? Should you be using machine learning? Is this an appropriate solution to your problems? Because it's popular these days, the answer tends to be yes. I want to do machine learning. Fantastic. Machine learning is a huge, huge field. You can use neural networks, you can use support vector machines, you can use random forests, you can use hybrids of all of these together, you can use algorithms that haven't even been invented yet as part of your machine learning. And the goal, I want a model for house prices. I don't want a dissertation on the sensitivity of neural networks to all these basic parameters. And I certainly don't want a chain of algorithms to feed into the next, because I want to go straight to the goal. And so you can reach this point where you're so caught up on the problem, and as engineers we like solving problems. And once we say, well, I've got this solution, but the problem is one of them works better than the other and I don't know which one's right. Okay, so now my problem is I need to decide which one to use. Well, no, the problem is modeling house prices. And you can ask, well, what are the important metrics? Am I using mean squared error, max absolute error, percentage error? What should I be using? And if we have multiple metrics, what am I going to do when two of them compete? Take the average? There's no reason why you can stop at 2 if you're just going to take the average. Build 20 neural networks. Build 1,000. Where should you stop? But you could get into other ways rather than building this classifier to decide which neural network to use. You can increase the number of nodes, you can increase the number of layers, you can do sensitivity to different inputs, scale your inputs. There's all kinds of different things you can do to try to solve this problem. But even if you were to solve this exactly, this is a simple model to begin with. Even if you solve it exactly, you're not taking into account whether or not you're pursuing the customer for the extra $40,000. You're not taking into account what may be tens of thousands of dollars in fees to process this. And again, if your model correctly predicts that house prices are going up, to a certain extent, it doesn't matter by how much. And for these data in particular, it's forecasting the median value. So for any individual house, there's a 50% chance that you're too low and a 50% chance that you're too high, even if you've done it perfectly. So here's where I'm going to divert from kind of the standard development methodology that most of you would then make some decisions of how you're going to resolve this conflict and run your test data and compare. And what I'm advocating is try not to do that. So you've agreed on how you're going to assess it. You've agreed on on what you're doing is theoretically sound, and now you should be ready for validation. Now, in many of your cases, you might not be familiar with the principles of validation, so I'll quickly take you through that, and from the context of my work in defense. So the first basic questions of a validation context is, was it developed according to your processes? There's an implication here that you have a process by which you develop models, which may be alien to some of you. And I'm not talking about the standard, well, you get your data, you clean your data, you do some single factor analysis, you multi-factor, you run your test, right? And is the model fit for purpose? Now, I said in the beginning that my purpose for this model is to have it be reproducible so that all of you can do it, to use open source data. And so for that purpose, yes, this is fit for purpose. For purposes of predicting house prices in Australia, these are Boston house prices from the 1970s. And it's not a time series. There's no variation in this over time. I can't actually use this to predict whether prices are going to go down next year. So you can run into these instances where I've used machine learning to model house prices, but not in the way that I need to for the problem of estimating loss given default at a bank. For the purpose of explaining it to you, for the purpose of all of you being able to go out and reproduce what I've done, it's fit for purpose. For the purposes of estimating LGD, not so much. So from a validation point of view, you really need to re-examine what the purpose is of your model, because the same data, the same model, can both be fit for some purposes and not others. If we go to a defense context, it gets a little bit more than that, which is your data even appropriate? In a defense context, this is difficult because if I'm writing an algorithm to recognize tanks, I can't exactly call people up and say, hey, could you park a tank like in the middle of a field, and one in the desert and one in the mountain, one in the forest, and I'm going to fly my high-res sensors around it. Could you just leave it there for me? And I'll just do that, please? I mean, I know our countries aren't on good terms, but I really would like some data. Can I do that? And so while you can laugh about that in a defense context, if you're modeling house prices in Australia, Australia's gone 26 years without a severe recession. The bank only really cares when times are hard. Where am I going to get severe recession data for Australia? I certainly don't want to cause a recession tomorrow, so I get my data. So you need to do something. You can get data from somewhere else. I can use US data, but the US and Australia are very different. I live here now, right? You can use data from the UK and say the UK is closer to Australia, and people may agree, but the sizes are so different. Where are you going to get data to try to estimate what a recession looks like? And then secondly, have you considered adversarial impacts? So adversarial impacts take a larger context in defense. So what I mean by adversarial impacts is you implement a model, and what you're modeling changes. That's what I mean by an adversarial response. So you take your example of the tank, you get some sensor data from a tank somewhere, and you can use heat signatures to find tanks. So you look for big bright things because tanks tend to be metal. They tend to reflect the sun and get hot. And so you go out there and you look for them. But I mean, I know that you can use heat to find tanks. So I want to make my tank look less hot. And now you need two models, one for a hot tank and one for a less hot tank, or one that's camouflaged. So in this picture, there's two tanks. Before it was kind of funny when I said, well, let's build two models and let's classify which one I want to use when. Well, you might have different models for hot tanks and cold tanks. In particular, the tank number 1 on the right is quite clear. Tank number 2, if it's not labeled, looks quite close to the background imagery. But now I found this on the internet. So the people who build this camouflage know that I know that there's camouflage. So now they want to make their camouflage look less like that, so that my model of that will break, so that I can't find their tanks anymore. And you can play this game as long as you'd like. So while it sounds kind of funny when I was talking about this chain of detecting house prices, once you start to consider the fact that what you're modeling changes, suddenly you can see this going around in circles several times. And in a machine learning context, there's a paper by several rather big name people from Google, Facebook, etc., that have found that if you have some images, so on the left there's a raw image that comes from the ImageNet database, in the middle is a magnified version of the chain, and on the right is the delta image. And I personally can't tell the difference between the left side of A and B, right? That the little dog still looks like a little dog, etc. And you train your neural network and you evaluate its test performance, and it manages to get all of these correct. So then you take the ones on the right, which you've modified slightly in some adversarial response, and it misses all of these. And in fact, it thinks that all of those are ostriches. How? Why? If I were using traditional image processing techniques, then I would extract features from some of these, and maybe I find a little white patch on the dog, and the little white patch of the wing is where it's confused. But with a neural network, I don't know where to start. And you may say, well, there's this long line, and that's a long line of the bust and the temple or whatever. But in machine learning, one of the problems is the explainability, that when I get an answer that I don't understand, how do I convey that? How do I explain to my manager why my way to find a tank just failed and I've blown up a school bus? How do I get through this? So you can do things the other way. So this says if I make a very small change, I can throw off the classification. The other way is I want to get something that looks the least like the target and fool you. And so you can ask the question, well, if machine learning can do anything, can machine learning design a problem that machine learning can't solve? Because if your answer is yes, then, well, machine learning can't do anything. There's a problem it can't solve. And if your answer is no, it's like, oh, well, then the problem you need to solve is finding one that it can't do it. So they've done this, where you take your image database, you train a deep neural network, and on the right-hand side, you have a genetic algorithm. And you play the game like this. You pick an image. The right-hand side picks an image, which could be one of your true images or one of these sets of wavy lines. You feed it into the neural network. The neural network comes out with a percentage. And in particular, note that the wavy lines on the left, it thinks is a guitar with 99.99% probability, which is more confidence than it thinks the guitar is a guitar. You update your labels. The genetic algorithm gets to make a new image. The neural network updates all its weights so it won't be fooled again, and you play again. And you keep doing this, and the mathematics shows that this will always be able to find an image based on some regular patterns that will fool the neural network. So this is the basic idea behind AlphaGo, if you know about AlphaGo, where instead of hooking it up to a neural network and a genetic algorithm, you hook the neural network up to itself and you say play. And it wins and loses. It updates the weights and plays again. And you do this millions and millions and millions of times, and it beats itself and loses to itself millions and millions of times. And at the end of the day, you hope your neural network is good enough to beat a person. Now you may say, well, that's nice, Craig, but I don't work in defense. Why do I need to worry about this? So you can game website analytics. So I go to a website, I know they're tracking me, or they could be tracking me, and I want an item, but I don't need it now. So I add it to my cart, and I read the reviews, and I look at shipping costs to Australia, and then I remove it from my cart and delete it. And sometimes after a couple weeks, I'll get an email saying, hey, just to let you know, this item's just gone on sale, 20% off. And another way to do it is, I'm American, I fly to the US on a regular basis, once a year. I'll look at flights on Chrome, I'll get a price, I'll go incognito, I'll go to the same website, and sometimes I get a different price. Because I know they're looking at me. And I know from my time in defense that if they're modeling me, I can try to avoid it. My wife's French. When we fly to France, her computer and my computer will give us different prices. we take the lower one. And if you wanted another example, I feel fun talking about this at Microsoft, you can turn chatbots into trolls. Where, Baron Meanington here has the nice question of, do you support genocide? This question is adversarial. I mean, could you imagine going into a party? Yes, hi, my name's Craig, nice to meet you. Do you support genocide? You can further be adversarial because Baron Meanington here could first tweet at Tay, hey Tay, I really love genocide. I really wish more people would support it. And then delete the tweet. But Tay's heard you. Do it again. Create accounts and just tweet how great genocide is at Tay. Delete all those tweets, delete all those accounts. Get on your main account. Hey Tay, do you support genocide? For no reason other than to take a screenshot of this tweet and send it to the BBC. Because he's got nothing better to do. But even so, okay. We want to train our machine learning algorithm. What's the right answer to the question, do you support genocide? I do indeed probably isn't right. Your Microsoft, you said that you're trying to encourage interaction with Tay here. Do you ignore this? Do you say no, of course not? Just a stern no? How about the only genocide I believe in is the elimination of internet trolls? Do you happen to know any? If you're going to train this machine learning algorithm, what is the right answer to this question? How would you evaluate it? How would you score it? And this other person has said, well, come on, let the algorithm learn. Put it back online. Let it figure out what's right and wrong. And let's move this learning forward. I actually agree with this. So, from the point of view of validation, it's important to note that machine learning occurs after data science. So although this community summit was machine learning and data science, I actually think that's backward. It should be data science and machine learning. Because from a defense context, getting good data is hard. And if your data isn't accurately representing what you're trying to solve, you're not going to get good results. And even if you have your data, and your data is really nice, if you get an outlier or you get a missing value, what are you going to do with it? Even if your training data doesn't have any, you should be ready. Because when you observe something, you may change it. In a defense context, that means someone's modeled something that they don't want you to see, and they've made something that you didn't expect, and you've just got a model with a response that was outside anything you could have predicted, but now what should you do? One of the quickest ways I've heard economics explained is if you change the incentives, people behave differently. And that's just true once you start to model them. But so let's say you've answered all these questions. And you know what you're confident that your model's right. And so now you should run your test data and see what's going on. Because if you have outliers or missing values in your test data, even though you had none in your in your training set, you should be ready to go. And I'm going to advocate to go ahead and hold off. And your training results should be ready for governance. So now I want to talk about what governance means within the context of biomedical engineering. So by governance, it's okay, you've built your model, it's been validated, but now what do you need to do? So I was working on the code for the bionic eye. The code gets approved, signed off. Yes, Craig, your code's good. It gets converted into software, burnt onto a chip, and surgically implanted into the eye of the study participant. I can't do this. I'm not a surgeon. What will it take to put this device in a person? So what sign-offs do you need? Who has the authority to do this? And how are you going to monitor the model? So from biology, there's regulatory bodies. In Australia, it's the Therapeutic Goods Administration. And then there's ethical questions. You're doing this to help people. Will it? How do you know? So there are standards about this. This is an online version of what's called IEC 62304, which talks about software for medical devices. And it has some key points regarding the development, validation, and governance. If you're going to take your model, code it up into software, and use it on a person. So when you're going through the development, there's a standard. There's 8 steps that you have a plan, you have requirements, you have an architecture and detailed design, you do unit integration and system testing, risk management, problem resolution. And then you get down to whether or not you need ethics approval. In the case of the bionic eye, one of the first implantees, Dr. Diane Ashworth, is an academic in her own right, and she understands all of this. And if you read her book, she talks about kind of the interaction with all of the engineers, such as me, and them making sure that she was going to be okay. Because you're doing this to help people. And the next part is this maintenance, this governance. You put the device in, you turn it on. It's working. Fantastic. You want to update it. You want to add new functionality. You want to give the person who's using your device more capabilities. You want to upgrade it. How do you know the upgrade's good? On the bad side, you put it in, you turn it on, and it does nothing. The patient can't tell the difference between when the unit's on and when it's not. What do? Do you take it out? That's another surgery in itself. Do you leave it there forever? Do you turn up the current? When you start getting results about how your model is performing, what do? So when I say that your training results should be ready for governance, this is what I mean. The mean squared error for my neural network was about 5, without getting into the selected case. When I run my test results, I expect it to be higher. How much higher? 6? 10? 200 is too much. If it were 200, what would you do? Pull it out? Modify it? Go back to something that's not machine learning? How much is too much of it not working? And if you hit that, what are you going to do? So this may seem like it's a big burden, but it is best practice. And if you take a step back and consider performing experiments on a human being, shouldn't you hold yourself to the highest standard? Now, if agile methodologies are shown to be better than this, if other development paradigms start to come out, this should be updated according to whatever is best, because you're playing with someone's life. With that in mind, things still go wrong. In biology, it's going to mean people die. You're doing this to help people, and you hurt someone. Now what? You can ask the question, what did we do wrong? There's a little bit of a false choice here, because frequently when you're given 2 options, people like to think, well, yes or no, one's right, one's wrong. They could both be wrong. It could be you do nothing to help the person and they die, or you do your best to help them and they die anyway. What could we have done better? You may ask yourself. I say you may ask yourself, but I'm very careful to say we in both of these. Because this idea that you have your development, then you have validation, then you have governance, this burden should never fall to any one person. especially not me. And you can ask yourself, what if I had? I said earlier that it's important that you consider whether or not your questions are fit for purpose. And while I can't tell you the right questions, this is the wrong one. Spent many years of my life stuck on this question. And as I get older and move into management, I care less and less about neural networks and support vector machines, and whether or not your deep neural network should have 12 layers of 15 or 8, or how many nodes you have, or what kernel function is best for a support vector machine. And instead, it's helping young people navigate questions like this. I said the greatest pitfall was assuming that or the greatest mistake was assuming your pitfalls would be technical. But at the end of the day, machine learning can't answer these questions. So what is important to you? What are you doing about it? So if I recap all of this, when you're moving through to development, you should always be asking yourself, is this the solution appropriate for your problem? And by appropriate, I don't only mean whether or not it's correct. There's technically correct, and then there's whether or not things are right. And I encourage you to consider that. And try to remain focused on the goal, not the algorithm. And this can be hard if you're working through a PhD and you've got your algorithm, which you have been working at religiously for the past 3 years. And then someone comes up with something better. Or you reanalyze things and decide maybe there's a faster way to do it. From a validation point of view, I don't care how good your algorithm is, you need good data behind it. So these self-driving cars, which you may have heard about, right? Google has these self-driving cars. I'll make you a deal. You can have all of their machine learning algorithms. You can have them all. I get their sensors. And we'll see who can build something first. I would much rather be in a position where I have the data and need to be able to analyze it than to have this fantastic algorithm that just needs the inputs. Because everyone talks about the ability to process quickly, but high quality LiDARs being available on a commercial scale is relatively recent. And from a validation point of view, keep in mind that when you start measuring something, you may change it. From a governance point of view, there's a question of, can you do this? Is it legal? Is it ethical? Is this something that you can do? And furthermore, you should ask yourself, can you do this? Because if you fail, are you prepared? Thank you.